Okay. Hi everyone. My name is Kimiya, and today I want to present our work on exploring adaptive MCTS with TD learning in miniXCOM. Just a second, I will share my webcam as well. Okay, there. So in the last decades, the use of deep learning has shown many improvements in AI agents. However, not all game-playing AI agents can access the environment for pre-training. The limitation of access to the environment and the computational resources needed in deep learning indicates the need to research and improve the non-deep learning algorithms for more practical uses. One of the most important aspects of an AI agent in a competitive environment is how it adapts to the opponent's strategy and learns to react appropriately based on that. Finding a way to react to opponent's action in an online manner without pre-training and accessing the environment beforehand is an interesting area of research. In our work, we focus on two popular algorithms that is frequently used in game-playing agents, MCTS and TD learning. We explore the research question of whether MCTS can be guided by reinforcement learning so that an AI agent can effectively adapt to its opponent's strategy while playing. We propose MCTS-TD, which is an improved version of MCTS that utilizes the TD update to estimate state values and guide the search. Also, we present evaluation of MCTS in a turn-based zero-sum game named miniXCOM. MCTS is a popular algorithm in game-playing agent that has been used in many board games like checkers and Go. MCTS works online and doesn't need pre-training. Also, it's an anytime algorithm where you can stop the process at any time and get some kind of a solution. These characteristics make MCTS an ideal candidate for our application. The basis of MCTS algorithm includes building an asymmetric tree and searching for the optimal solution while simulating the game. In MCTS, there are four general steps: selection, where node is selected; expansion, the selected node will expand into one or more children; rollout, the game is simulated and the results are used to assign a score to the current node; and backpropagation at last, where the score is gathered from the simulation is backpropagated from the current node to the root. A common selection criteria used in MCTS is UCT, where a new node is chosen based on the equation that is shown in these slides. QV is the current total value at node V, and NV is the number of times node V has been visited in the selection step. C is the constant chosen to control the rate of exploration. The two terms in the equation combine the advantage of choosing the node with the highest value with the exploration of the nodes that are not visited frequently. The reinforcement learning algorithms aim to maximize the cumulative reward that is gathered by the agent when taking actions in the environment. Temporal difference learning, or TD, is a popular model-free reinforcement learning algorithm that uses a technique called bootstrapping. In bootstrapping, the state values are estimated based on next state value current estimate, and there is no need to wait until the end of the game to be able to estimate a state value. One of the successes of TD learning is TD Gammon agent, which was able to play at championship level of backgammon. Also, many today state-of-the-art reinforcement learning algorithms use TD learning as part of their process. An example would be the famous DQN algorithm, which can learn policies with high-dimensional inputs. The core idea behind TD learning is that the utility value of a state, or UST, is calculated by using the next state utility value current estimation. In this equation, alpha is the learning rate and gamma is the discount factor of the estimated future state value. The MCTS algorithm and its variation have been used in many games, including commercial video games like StarCraft. MCTS has been successfully deployed in the imperfect information card game Cribbage and board game Terraforming Mars. Reinforcement learning, or RL, has many applications, including game-playing AI agents like DQN. Besides that, RL has been applied to many other gaming applications like procedural content generation tasks, game design, and automated test challenges. Moving on to algorithms that stand in the intersection of MCTS and reinforcement learning, one of the most prominent algorithms that uses a combination of RL and MCTS algorithm is AlphaGo. AlphaGo uses two neural networks for policy and value functions. During online play, the neural networks continue to be refined by using a UCT-like algorithm. This algorithm was able to defeat the best human players in Go. Next, Ilhan and Itene Uyer at 2017 proposed an approach that used MCTS rollouts as the agent's past experience and used this past experience in their oral algorithm. They assumed that the forward model of the environment was accessible, which is not the case in our application as we cannot predict the opponent's actions. Boydo Pivek at 2017 designed an algorithm based on a TD tree search framework named SARSA UCT, which used UCT as the MCTS algorithm and SARSA as the reinforcement learning part. They were able to show that bootstrapping and TD backups were beneficial over MC backups in an MCTS-like search. In our proposed work, MCTS backups are not replaced by TD. Instead, our algorithm uses TD as a guide for the MCTS algorithm. Our proposed method is MCTS-TD. In MCTS-TD, the MCTS algorithm is guided with TD learning to help the agent adapt to the opponent's strategy. The algorithm includes three main functions: select node, rollout, and backpropagate. Note that the select node corresponds to both selection and expansion phases in MCTS. There is a main difference between original MCTS and MCTS-TD. As you can see, the selection criteria in function best child is different from UCT. A new term is added to UCT selection criteria, DUASV prime. U is the utility value of the child estimated by the update function. D is the TD factor, which is used to control the effect of utility estimation in the equation. The higher utility value of a child estimate is, the more chance it will get to be picked. The update function is the function responsible for estimating the utility values of the state. This function is called 2 times per step, once after the agent does its action and receives a reward, and once after the opponent's action to account for opponent's actions as well. As you can see in the slides, update function will estimate the utility of the state by using the TD learning update. For our experiments, we use miniXCOM, which is a turn-based game inspired by XCOM franchise. There are 2 players in this game and they compete to win. Each player has a squad of soldiers that they can control in a pre-designed map. There are walls in the map that can block the shooting of squad members. In each turn, one player has the ability to control their squad. A squad member can move to a new empty spot, shoot if an enemy is in line of sight, meaning that there is no walls blocking the shoot in the way. And lastly, the squad member can combine these 2 actions and move and shoot immediately afterward. Moving to a grid is possible if there is a path to it, and getting there doesn't exceed a fixed number of steps. Shooting is possible if other squad member is an enemy and they are in line of sight. Shooting will kill the enemy and remove a player's squad member from the board. A player wins when there are no enemy squad members left. For our experiments, we compare MCTS-TD with the original MCTS, SARSA UCT, and a rule-based agent RB1. MCTS-TD agent implements our proposed method. MCTS agent is the original version of MCTS without TD learning. As we talked about, SARSA UCT is an algorithm that combines SARSA with UCT in a way that MCTS backups are combined with reinforcement learning estimates. This agent is different from our proposed algorithm as we don't combine the MCTS backup values. MCTS-TD only alters the selection phase and guides the selection using reinforcement learning. Lastly, RB1, which is a rule-based agent that always picks the left corridor on the grid to launch its attack. If there is an enemy in the line of sight, RB1 always shoots at them. If there are multiple enemies, it will choose randomly. Otherwise, it moves to the leftmost member to the left corridor. Our experiment grid is 6 by 6 with 2 squad members on each side. In each round, 50 rounds were played and a total of 20 rounds was repeated. The two sides took turns in making the first move, each side going first in 25 rounds. A round ends in a draw after no winning after 20 moves. Our configuration is as follows. We had the TD factor as 1, learning rate 0.8, and exploration constant for MCTS was 1 divided by the square root of 2. These values were kept consistent throughout the runs. The representation of this state space is a 3x3 grid centered around the current location of the most recently moved squad member. This is the result of playing MCTS-TD versus RB1. This is shown by the number of wins. In the first 10 rounds, the two algorithms are matched, and from that point onward, MCTS-TD adapts to the opponent's strategy and outperforms RB1. Note that the gray lines on the diagram shows the standard deviations. Next, we can see the results of MCTS-TD versus SARSA-UCT in this figure. MCTS-TD has a clear advantage over SARSA-UCT from the start and is able to outperform SARSA-UCT. This figure shows the results of MCTS-TD versus original MCTS. Although the winning rate of MCTS-TD is lower here compared to the last experiments, the MCTS-TD is able to outperform MCTS from the start. This table shows the combined total results of the experiment. The winning rate is the numbers of wins per 10 rounds averaged over 20 rounds. The standard deviations are shown in the brackets. As you can see, MCTS-TD outperforms our three other agents by winning respectively 6.67, 6.11, and 5.55 out of 10 against RB1, SARSA-UCT, and MCTS. In this work, we focus on game-playing agents that can adapt to the opponent's strategy online without pre-training by proposing a new method called MCTS-TD. We combined original MCTS with TD learning and showed how MCTS-TD outperforms original MCTS, a rule-based agent, and SARSA-UCT in a turn-based game. In this work, we use the compressed representation of this state. However, the future work should explore other representation of these states for more complex maps. For example, the process of extracting features from the environment to represent the state can be automated using deep learning. MCTS-TD is not only designed for games and can be used in other domains as well, and future work can examine the application of MCTS-TD in other domains. Thank you for listening to me, and let me know if you have any questions.